Hello and welcome. This is SFU Math 232. It's Brennan Davison. I'm going to talk today about section 6.2, the geometry of linear operators. We're just going to cover the version in R2. We're not going to cover the whole thing again in R3. So we'll just head up to the section, the end to the end of R2. So we're going to see a few new terms, again, some more vocabulary, and that certain matrices, there's certain types of matrices can only perform certain linear operations. Okay, so let's see what we mean here. We're going to have a new term, orthogonal operator. And what do we mean by that? If we have a linear operator, so we know what the characteristics of being linear are, and it's length preserving, which means that if we operate on the vector and then we take the norm, that's equal to the norm of the vector. So by whatever operation we perform, we don't change the length of the vector. So that's what we call length preserving, does not change the length. We call that an orthogonal operator or a linear isometry. I'm going to use this term most frequently, an orthogonal operator. Okay, so we've got some operations here, what we saw last lecture, what some of the possible linear transformations in R2 can be. We can rotate by phi about the origin, we can reflect about a line through the origin, and we can project onto a line through the origin. Okay, and some of those are which ones, so the idea here is which ones are length preserving, does not affect the length of the vector. So let us just draw these three things out and remember what they are. We can answer that question and then notice what's coming. Get a foreshadowing of what's coming. Here's a vector x. Now I imagine I rotate that vector by some angle phi. And then the vector is over here, rotated by phi. Okay, so I take the vector, I rotate it by phi. Does that change the length? No, it does not, right? I just took it and I rotated it. It does not change the length. I'm just going to remind you of the standard matrix of rotation by an angle phi. It looks like this: cosine phi minus sine phi, sine phi, cosine phi. So that is a length preserving rotation by phi. So rotation is length preserving. Okay, how about if we do a reflection? Let's take that same vector x and reflect it about an angle theta. So I don't know. Let's just make some angle here, some line here of length of angle here theta to the origin, and then let me take that vector x and rotate it about that line. So when I do that, it's going to be, I'm going to go, there's some angle here. I'm going to make that angle right here, and then I'm going to have x right here like that. So this angle here and this angle here are the same. So I'm going to reflect x about that red line. That is a reflection. And same thing here. You can see I've taken the vector, I've just reflected it over. There is no change to the length. So this one, reflection, is also length preserving. And that we will recall that the matrix for that looks like this: cos 2 theta, sine 2 theta, sine 2 theta, and minus cos 2 theta. Okay, so those are two length preserving transformations in R2. And then let's look at the projection onto a line through the origin. Well, let's just take a look at that, remind ourselves what that is. So if I've got a line through the origin, and then I'm going to take some vector x. I'll make the guy black here. So it'll be like, say I get this guy here, x, like that. Now I wish to project x orthogonally onto the line, the blue line that is going through the origin. So I go here at 90 degrees, come like that, and then right down here is this right here is the projection of x onto L1. Let's just call this L1. Now, is that length preserving? No, it is not. You can see that the vector, the projection there is, in this case, it is shorter than the original vector. Okay, so this is not, no, it's not length preserving. Okay, so let us just write the matrix for that. This line here being at an angle phi from the positive x-axis. So this one here is cos squared phi, sine phi, cos phi, sine phi, cos phi, and sine squared phi. Okay, so just as we're going to move on here, we have two that are length preserving and one that is not. We have the standard matrices written down. What do you see? Can you observe anything about the matrices? That's the first question. Any observation about the matrices? Okay. All right. Let's get some tools in place. So here's the theorem. If T is length preserving, sorry, let me say it again. We have start with T, a linear operator, and then if T is length preserving, it also is dot product preserving. If it's dot product preserving, it is also length preserving. Okay, so this is one of those if and only if proofs. It works both ways. We can maybe recall what is length preserving from the previous slide. Length preserving means, let's just get the meaning of this guy written right here. Length preserving means that the norm of T of x is equal to the norm of x. That's for all x in Rn. Okay, so we're going to prove this one. So we're going to do both directions. One direction is very quick. The other direction takes a bit more work. So let's go in the more work direction first. We'll start with the assuming that the transformation is length preserving. Now what we want to do is show that the dot product is preserved under the transformation. And so what we're going to do is we're starting there, and then what we're going to do is we're going to take two vectors, x and y, in Rn. And let us just recall what the dot product is. X dot y looks like this. First component of x multiplied by the first component of y plus the second component of x multiplied by the second component of y, all the way along to the nth components. Okay, let's take a look at what the norm of x plus y looks like. The norm of x plus y is the square root of x1 plus y1 squared plus dot 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 plus xn plus yn squared. And the norm of x minus y is similarly the square root of x minus x1 minus y1 squared plus dot 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 plus xn minus yn squared. Okay, now that is here. What is that? That is the square root, this one here, the square root of x plus y dot x plus y. Okay, we saw that directly from here earlier on. And similarly, this one here is the square root of x minus y dot product with x minus y. Okay, So I can now take the difference of these two things, the norm of x plus y minus, in fact, I'm going to do the squares of them, of x minus y squared. That's going to be equal to x plus y dot x plus y minus x minus y dot x minus y. Okay, so then we can distribute and do a whole bunch of canceling, and so it basically is algebra here. This is distribution and then putting together like terms, and you will find that this is 4 times x dot y. Stop the video, fill in those steps for yourself, make sure I didn't make a mistake. So that tells me then that x dot y is equal to 1/4 of the norm of x plus y minus the norm of x minus y. These guys are squared. Okay. Okay, I'm going to use that. Now, next, let's take a look at t. Let's think here. How do I want to do this? Okay, I'm going to go like this. Let's take a look at the transform of x dot the transform of y. That's going to be equal to the transform of x1. Let's try that again. That's going to be the, when I take the dot product, that's going to be the transform of x1 times the transform of y1 plus, and I go through them all like that, transform of xn times the transform of yn. Okay. Then that will be equal to the transform of x1 y1 plus dot 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 plus the transform of xn yn. And what is that? That is the transform of x dot y dot. And that, because of this identity right here, is the transform of 1/4 of the norm of x plus y squared minus the norm of x minus y squared. Okay. All right, now though, however, let's look at what we've got happening here. We have a linear transform. So now I can write this here using the linearity properties as 1/4 the transform of the norm of x plus y squared minus the transform, and there'll be a bracket here, transform of x minus y squared, like that. And then we know that this transformation is length preserving because we have that sitting right here. It is length preserving. So that is equal then here to, by the length preserving property, this guy here. And that is equal to x dot y dot. Okay, so we now have that we have the start of this whole thing, this guy here, and we've ended up with that equal to that over here. That's what we wanted to show. We started with the assumption that it was length preserving, and now we have that the dot product is preserved. Okay, now we're going to go the other way. I've used up a bit too much of the space here, so let me just move this down a little bit, and I'll do it here. So now we're going to go the other way. So we'll do this example afterwards. We're going to assume that it's dot product preserving. So we're going to assume the second piece here, that is this guy right here, which we just showed. So we're going to assume that and go the other way. So we assume this guy here. like that. And then we will recall that this is the norm of x is the square root of the dot product. And so then the norm of t of x is equal to this thing here, t of x dot t of x, like that. And that is equal to the norm of x. And we're done. It's length length preserving. So we're finished. Okay, so theorem is in place. Okay, now we're going to just use that to show this example here. So we want to show that an orthogonal operator preserves angles. So what we're going to do is notice. So what we want to do is we say what we're doing here is we're saying we have two vectors. Let's call them x and y, like that. And we perform an orthogonal operator on them. Let us, for sake of illustration, imagine that we do the rotation by phi degrees. So I'm going to rotate this thing here, right here. I'm going to try to I want to make it the same length, of course, so try to make it look the same length. So I'm going to rotate that guy by phi. I'm also going to rotate this guy by phi. So that angle, those angles are the same. So that is, let's call that x prime and y prime. So each one of them has been operated on by the rotation operator, which is length preserving. And then what we want to see here is that the angle between x and y originally, this angle right here, that angle, which let's maybe just call that theta, we want to show that after doing this orthogonal operation, that angle is sitting also there. That angle is still theta. It didn't change from this operation. So I've taken two vectors. They were a certain angle apart. I've rotated them both by phi, and the two vectors themselves are still angle theta apart. That's not surprising when you see it geometrically, but let's just go ahead and apply the theorem so we can see this algebraically. Okay, so you will recall that the angle between two vectors, theta, is the inverse cosine of x dot y divided by the norm of x times the norm of y. Okay, so now we imagine calculating the angle between the transformed vectors. That will be the angle between the transformed vector x and the transformed vector y. We will calculate that in the way we always calculate angles between vectors, like this. Okay, and then what can we say? Well, the dot product is preserved. So I'm looking at the numerator. The dot product is preserved. So this is x dot y. And then I look in the denominator, and it's an orthogonal transformation, and orthogonal transformations are norm preserving. They don't change the length. Okay, and I see that these two are equal. So the angle between my two transformed vectors is the same as the angle between the original vectors. Okay. So next thing we're going to talk about is we've got an orthogonal operator. We're going to ask, what does a standard matrix look like? Is there some characteristics of this matrix when we've got an orthogonal transformation that will allow us to identify that? And indeed, the answer to that is yes. So a square matrix is orthogonal if AA transpose is I. Okay, or you can write that equivalently this way, if A inverse equals A transpose. If that is the case, there are other properties that A will have. Its transpose will be orthogonal, its inverse will be orthogonal, importantly, the determinant will be plus or minus 1. And if we have some other orthogonal matrix, the product of the two of them will be orthogonal. Okay, all of these are actually pretty straightforward to show. So these are straightforward to show. Okay, so I highly recommend try them yourself. Stop the video, kind of treat it like a test. I'll start with the definition of an orthogonal matrix, and then see if you can show all of these properties. It's done in the textbook, so you can check yourself. So page 282 of the Busby textbook has these proofs. They're all quite short, and you know, it allows you to sort of recall these sort of things. So there's a bunch of things we have seen earlier in the course, these properties that come in useful here, that you want to sort of remind yourself of. Okay, all right. So go ahead and do that, and then check yourself. Okay, so let's just take an example here. We've got the rotation about the origin. That we have the matrix for that. It looks like this, where we're going to rotate 5 degrees about the origin. Our matrix looks like that. Okay, and let's take the determinant of that matrix. Determinant of R phi, that will be cos squared phi plus sine squared phi, and that is 1. Okay, so we can then claim here that R phi is an orthogonal matrix. We're going to see this come up again. Okay, another theorem. So we've got an n by m matrix. The following statements are equivalent. If it's orthogonal, it's norm length preserving, it's dot product preserving, the column vectors are orthonormal, and the row vectors are orthonormal. Okay, so we follow that up with a statement that that if we have a orthogonal linear operator, then, and we also have the standard matrix of that transformation, then if one of them is orthogonal, the other one is. It's an if and only if. Okay, so this is basically saying if your transformation is orthogonal, that tells you that the matrix that that captures that transformation, the standard matrix, maybe I'll put that way, standard, is orthogonal. And it's also telling you that if you have a standard matrix transformation that's orthogonal, then that your linear operator is orthogonal. Okay, so we've already showed, for example, we showed that R of phi, which was this guy here, cos phi, sine phi, minus sine phi, cos phi, that guy, we showed that the determinant of this was equal to 1. We could also take R phi transpose, multiply it by R phi. That will, let's just quickly do that. That'll be cos phi sine phi minus sine phi cos phi. Then I'll multiply by the transpose. Cos phi minus sine cos phi. Okay, that becomes this here, cos squared phi plus sine squared phi, 0, 0, sine squared phi plus cos squared phi. That is equal to this here. So we have that R phi transpose, R phi is I, the identity matrix, the definition of orthogonal. Okay, let's just take just as further example of these properties here, let's look at the column vectors. of this matrix. So the column vectors of R phi. Let us just take a look at those. There's two columns. Column 1 is this guy here, cos phi, sine phi. Column 2 is this guy here, minus sine phi, cos phi, like that. And so, I mean, they should be orthonormal. So let us take the dot product and see if they're orthogonal. So I take the dot product of these two, and I get 0. So they're orthogonal. And then I compute the length of each one of them. And if I can compute the length of C1 first, that is the square root of cos squared plus sine squared, and that is 1. And then I take the length of the second one, and that is the square root of minus sine squared plus cos squared. That is also 1. So the two vectors have a dot product of 0. The length of both vectors is 1. C1 and C2 are orthonormal. Okay, next. Rotations and reflections, we saw it by drawing them out. They're orthogonal operators. They are length preserving and they are linear. So now we're going to say that this is a strong statement. If we've got a transformation from R2 to R2 and it's orthogonal and linear, then the standard matrix is one of these two. Think about this. There's only two possibilities. So it's, I guess in some sense, you can ask this question here, what can matrices do? Well, the orthogonal ones do one of these two things. They either rotate or reflect. Okay, so we already showed that the determinant, earlier we showed that the determinant of R of phi was 1. That was shown earlier. And then we have that the determinant of h phi, the reflection one, let's take the determinant here, that is cosine 2 phi, sine 2 phi, sine 2 phi, and minus cosine 2 phi. That's equal to minus cos squared 2 phi minus sine squared 2 phi, and that is equal to minus 1. Okay, so we have the determinant equal to minus 1. So in the first case we had the determinant equal to 1. The second case here we have the determinant equal to minus 1. The only two possibilities. Okay, a final slide. This is a short lecture. We have seen the two orthogonal standard matrices. Now, what about operations in R2 that are not orthogonal? So we'll contain them to doing one thing at a time. So these are going to be not length preserving. And here's an example. Here are some examples. Scaling with factor k. So what does scaling mean? Scaling means you simply have a vector like that, x, and then you multiply it by some scalar and it gets longer. And then this guy would be, say, for example, k times x. So it looks like k is about 3 there. So let's just do that example. We imagine we have a matrix that looks like this. A is equal to 3, 0, 0, 3. That scales a vector by 3 and doesn't change the direction. So if I take, for example, ax, I get this. (3x1) and then 3x2, which then I can write like this. Okay, so that vector A there scales my vector by a factor of 3. And you'll notice the determinant here is equal to 9. Determinant is not 1. Okay, and we can further classify this if we look at the more general case where A scales by a factor of k. We'll note that if k is between 0 and 1, it's a contraction, it gets shorter. And if k is bigger than 1, it's a dilation, it gets longer. Okay, so that's a possibility. That's not length preserving, and that is our scaling matrix. Then we have the idea of a vertical or horizontal compression and expansion. So we have two possibilities here. We have a matrix that looks like this, or possibly a matrix that looks like this. Okay, k is some number bigger than 0 and not equal to 1. So we have here horizontal compression, that is x changes by a constant factor and y stays unchanged. So my recommendation to you is to pick a number for k. I don't know, k equals 2 or k equals something like that. K equals 2 will do it, and then just multiply. Like, let's maybe label this like this A1 and A2. Multiply x times A1, multiply x times A2, draw x, draw A1x, draw A2x, and see what's happening geometrically. There's also some really nice illustrations in the textbook. This one here is vertical compression, or it doesn't have to, I guess, be compression. It could also grow bigger, so it could be expansion. Similarly here, that is just depending on the value of k, just like in the scaling thing. If k is less than 1, you get a compression. If k is bigger than 1, you get an expansion. Okay, then the other possibility is looking this one like this. Also is not length preserving. Looks like that, and coupled with that one is, call this say A3, and A4 is this one here. So this is a shear. So a shear in the x direction with factor k, or a shear in the y direction with factor k. So that means if you have it here, you have a vector here, you imagine, in fact, you could sort of imagine a bunch of vectors like this, and then what happens is after the operation has happened, your vectors are like this. Okay, that is a shear in the x direction, like that. And then similarly here, we imagine if we have vectors like this, then we apply a shear to it, we end up with your vectors being this way. Okay, so that's the horizontal and the vertical shear. So the main point here is that we have an idea of what is an orthogonal transformation. The fact that we then can define what is an orthogonal matrix, and then we recognize certain characteristics of the orthogonal matrix. Specifically, an important characteristic is that the determinant of an orthogonal matrix will be plus or minus 1. And then of the operations that we have looked at, we see that rotation and reflection are orthogonal transformations. They have orthogonal matrices associated with them, and that scaling or vertical compression, horizontal compression or expansion, and vertical and horizontal shear are linear transformations, but they are not length preserving, and their determinant will then necessarily there not be equal to 1 or minus 1. Okay, that is it. We are stopping here at the end of the R2 section. We're not covering the similar ideas in R3. Thanks, guys. I'll be back with the next lecture shortly. Bye.